Now, let me introduce our CGI acceleration flow based on C++ programming. Its primarily targets the acceleration of for loop written in C or C++, like the one shown in the code example. First, let's look at one target example, a computationally extensive for loop extracted from a CNN application suitable for acceleration on the CGI. Now, this kernel has multiple levels of nested loops, control logic, and arithmetic operations. So, when dealing with such a target kernel for acceleration, we first need to add parameters around this target for loop to help our front-end tool identify this kernel. Then this kernel is converted into the required DFG, data flow graph. Next, the DFG is mapped to the CGI. Now, let's show an example of the DFG generated by the front-end compilation. As shown in the above figure, we can see that it closely corresponds to the original code, including loop control and accumulation of intermediate variables, as well as conditional logic operations, e.g. if statements. Our architecture is a fused-grained design, where the fine-grained logic is highlighted with red lines in the DFG. Additionally, bit width annotations distinguish coarse-grained and fine-grained components. With this DFG, we then use our mapping tool to map the DFG onto our hardware. Let's run this process. Okay, after successful mapping, the mapping tool reports performance metrics, such as initiation interval and resource utilization. As mentioned earlier, our architecture is a fused-grained design. So coarse-grained operations are executed using ALUs, while fine-grained operations would incur high overhead if executed by ALUs. Thus, our architecture includes LUTs, lookup tables. Let's compare with this figure. The fine-grained operations we saw earlier are now fully converted into LUTs and mapped onto the architecture. After mapping, several key files are generated. The first is the executable file for CPU to invoke the CGI. The file consists of several parts. First, the CGI configuration bitstream, a long sequence of date. Next, CGI execution instructions, including loading the configuration date and configuring the CGI. Then, the next is instruction control to start the CGI computation. After that, results are written back to the main memory. These instructions complete the target loop acceleration. How does this CGI execution code run on the LCC? We need to integrate it into the target application code. And replace the original loop control with this execution code. Here is complete execution example. First, the SOC application code is divided into several parts. The first part initializes the required date. via 2 loops and prints relevant information. Next, the CPU executes the target loop once to generate reference results. We can see this loop matches the accelerated target loop, simulating the target loop encountered in the real-world task. The CPU executes it once. And if the target loop is to be accelerated by the CGRA, we simply replace the target loop kernel with the CGRA execution code. For verification, the CPU runs the loop first. Then the CGI executes the same loop. The cycle count for both are reported, and performance comparison can be made. The CGI execute file contains the bit stream and instructions generated by the mapping tool. At the end, the results are verified. There are 2 parts. The CPU's reference results and the CGI's results which are compared. If discrepancies are found, the verification reports an error. If correct, done is printed after verification. Next, let's explain the FPGA prototype of our CGRA. First, we boot Ubuntu. On the lower right of the screen is FPGA board, where the Fusion SoC is deployed. It's a Xilinx K-7 series board. The process involved programming the SoC bitstream onto the FPGA, enabling the FPGA to run the prototype. The board connects to the host via UART. The first while programs the SoC bitstream. And the second handles data exchange between the SoC and host. Once the FPGA runs the SoC, we program the compiled binary bitstream via UART. This configures SoC to execute the target operations. Okay, now we open the Vivado project to program the FPGA. We also power on the FPGA board and connect it to the host. Okay, now we program the SoC bitstream. Note that this is the SoC bitstream, not the CGI specific one. It deploys SoC onto the FPGA. The FPGA is now connected to the host. Next, we program the SoC bitstream. configuring the FPGA as our Fusion SoC design. Okay, programming is complete. Next, the compiled executable file is transmitted via UART to the SoC. To execute the full code on the prototype. This uses Berkeley's UART to TSI protocol for efficient binary transfer. For convenience, the command is displayed on screen. It transmits the executable file via UART. Let's check the results. Okay, the FPGA has completed accelerating the target loop kernel. Let's review the full workflow. First, date initialization. As mentioned earlier, it prints initialization complete afterward. Then CPU executes the loop, taking about 710,000 cycles. The CGI then executes the same loop, taking about 32,000 cycles. After execution, results are compared. They match exactly. The process completes. Compared to the CPU, the CGI achieves significant loop level speedup, reaching about 20 times acceleration. This concludes our SoC-based acceleration flow for C++ loop kernels.